Okay, well, thanks everyone for making it in the rain. I guess not feel it feels very much. I feel very much at home in this kind of weather. But I'm sure for those of you who grew up in California, it's a little bit alien. But there it is. Okay, so we're going to finish up some material from last time, where we've been talking about sampling algorithms for Bayes nets. We talked about sampling from the network itself, the prior sampling algorithm, the rejection sampling algorithm, where you throw away the samples that are not consistent with the evidence. We saw that that's incredibly wasteful, and the likelihood weighting algorithm is a way of ensuring that all your examples are consistent with the evidence, because you just fix the evidence variables. But you have to reweight the samples that you generate, and that can work well. But as we'll see, it doesn't work that well, particularly when you have a lot of evidence at the leaves of the network, because then you're generating samples, ignoring the evidence, and all of a sudden you get to the evidence variables, and the evidence variables say, that's ridiculous. You're hallucinating, right? Give it an extremely small weight. And then all your samples get a very small weight, except a few lucky ones that just happen to pick the right values. They end up dominating the estimates because they have exponentially larger weights than the other ones. And then you get very poor estimates because you've got an effective sample size of 1 or 2. So the Markov chain Monte Carlo, or MCMC, algorithms fix that problem, because not only do they fix the evidence variables, but they propagate information from the evidence variables, so that fairly soon you're actually sampling in a way that's influenced by all of the evidence, not just the evidence at the roots, but all of it. Information propagates throughout the network to influence the sampling. So in general, what is an MCMC algorithm? It just means you've got some space, and it's just like in search you have a state space. There is a state space for the MCMC, and it's just basically a way of wandering around randomly in that space. So it's a randomized algorithm that approximates something you're trying to calculate by following a Markov chain. So a Markov chain is just a sequence of states, and each new state is chosen randomly given the previous state. Okay? And you can have any neighborhood structure you want. You can hop from one side of the state space to the other in huge leaps if you want. As long as that random walk is constructed in the right way, your estimates will end up converging to the right value. So we'll see how that works. And in general, right, so there's two parts to the name. Markov chain means it's a specific way of generating samples by doing this random walk. Monte Carlo just means any algorithm that uses randomization to give approximate answers to a question. So the high-level picture of what is an MCMC algorithm, just wander around a bit and average what you see. So it's very, very simple, straightforward algorithm. So the particular version we're going to look at is called Gibbs sampling. And this goes back, this is named after a statistical physicist who worked, I think, around 1900 or something like that. It's a particular kind of MCMC that works by basically by sampling some subset of variables. Typically, in our case, we're just going to sample one variable, conditioned on the current values of all the other variables that define the state. So each state is going to be a complete assignment, and you leave the evidence variables fixed, and then you pick a variable, and we'll call the variable that we sample xi, and we're sampling a new value for it, so we'll call it xi primed, and it's sampled from the distribution for xi given the values that all the other variables have in this current state. Okay? And amazingly, that's all you need, right? Just pick a variable, sample its value, condition on all the other variables, right? These other variables here will include the evidence variable, right? So the evidence variable is E. And that's all you need, and then the algorithm will do this random walk, and the estimates that you get will converge to the correct values. Yes? Yes. So every variable, the evidence variables remain fixed. All the other variables have a particular value in each state. Okay, so the state is just the vector of values for all the variables. Okay? Well, you could have a partial assignment. So in the constraint satisfaction algorithms, like backtracking, right, you build the assignment by assigning one variable at a time, if you remember. But here we're only working with complete assignments. So this is more like the hill climbing algorithms, the simulated annealing algorithms. If you remember, right, you can do hill climbing or simulated annealing on n queens, but the states you're looking at have all the queens they have about, right? They're all in a particular place. If you run hill climbing on the n puzzle, like the 15 puzzle or the 8 puzzle, it's a particular state that you're operating with, okay? So this is the same basic idea. Okay, and if you think about it, right, by choosing to sample from the distribution of xi, given all the other variables, what's the most likely value that you're going to choose? Well, it's the one with the highest probability, right? Whichever value of xi is most likely given all the other variables, that's the one you're most likely to choose by definition, because you're sampling from that distribution. So that means that if you started out with a value for xi that wasn't particularly likely, given the other variables, you're likely to move to a new value that's more likely than the one you were in, okay? But you can also go downhill. You might start out with a high probability value, and now you're scrubbing that out, resampling it, and then you're possibly going to go downhill, right, and choose a new value that's less likely than the one you had before, okay? So in that sense, it's quite similar to simulated annealing. And if you're interested, you can, offline, see if you can construct a detailed analogy between Gibbs sampling and simulated annealing. Try and figure out, simulated annealing is different, right? It's got a temperature that changes. There's no temperature in Gibbs sampling. So it's different in certain ways, but you could try to construct the mapping. Okay. So then the next thing, right, so that's Gibbs sampling in general, is pick a variable, resample its value given all the other variables, okay? In BaseNets, that particular calculation turns out to be much easier than it might otherwise be in general, right? And that's because the probability of the variable given all the other values is equal to the probability of the variable given just the Markov blanket. Okay, what is the Markov blanket? It is the parents. I'm not sure why I didn't have this written on the slide, but anyway, the parents, the children, and the children's other parents. Okay, now there's a picture of that on the next slide, I think. So, so this Markov blanket satisfies this conditional independence assumption that given the Markov blanket, xi, the variable you're sampling, is independent of all the other variables in the BaseNet, given the value of the Markov blanket. So what does that mean? Well, why is that a good thing? It's a good thing because now, for the variable to sample its value, it's just looking at its neighbors, right? The parents, which are directly above, the children, which are directly below, the children's other parents, which are kind of your co-parents, if you like, right? The other adult members of your family. And so that's entirely local. So the complexity of doing this sampling operation is independent of the size of the network. So even if you have 1 billion variables in the network, right? So this list here is 999,999,999 variables, right? If you only have 2 children, 2 parents, and 2 co-parents, right? That's your sampling conditioned on just 6 variables. And so that computation can be done very easily, and it's independent of the size of the network. And because it's all local, right, you could even imagine it happening in parallel. You could be sampling all the variables of the network pretty much simultaneously, and asynchronously as well, right? And so some neuroscientists believe that, in fact, the brain is doing something like MCMC in a Bayes net. And they have evidence to prove it. But of course, other neuroscientists have evidence to prove their own theory of how the brain works. So it's still pretty much completely up for grabs. But there is evidence that the brain is pretty good at doing Bayesian parabolic inference. And so if you don't think it's doing MCMC, then you've got to come up with an argument, well, what is it doing that's managing to implement Bayesian parabolic inference, in parallel in a network that can only do local computation, right? And so it's actually not a completely implausible idea. Okay, as I said, if you just keep running this algorithm, right, pick a variable, sample it, pick a variable, sample it, pick a variable, sample it, and then you average the states that you see, whatever query you want, you just answer the query for that state, average the results, then in the limit of doing this infinitely often, Gibbs sampling is consistent, meaning it converges to the correct posterior probability given the evidence. Okay, and I'll go through some of the steps of that proof. I won't do the whole thing. I'll just sort of give you a flavor of what it's like, and the book has the whole proof in detail. Okay, so there's an asterisk here, which you probably can't see, but there's an asterisk there. And this is pretty common, actually. There should have been some asterisks in the same claim about the consistency of importance sampling. And there's some small print. So the small print is there. It says, provided all Gibbs distributions are bounded away from 0 and 1, and variable selection is fair. Okay, so bounded away from 0 and 1 is pretty clear, right? You can't have deterministic relationships in your network, because if you do, you can get stuck in some subset of states, then you can never reach the other subset. Okay, and so you're going to get wrong answers in that case. And variable selection is fair just means that eventually every variable gets sampled infinitely often. If you sample infinite many times, there isn't some variable that only gets sampled 3 times and you never sample it again. Okay? It's very easy to imagine how to do that. You could cycle, you could choose them at random and sample them, you could choose them in alphabetical order, you could do anything you want, right? As long as you're not starving some variable forever. Okay. So in fact, that's a useful, I'm now digressing slightly, right? Why might it be useful to sample some variables more than others? Yeah.
Maybe because other variables have larger dependencies on them. Then, like, they're more densely connected in a network than other sparsely connected nodes.
Yeah, because there's some variables are more important than other ones. Particularly, right, the one you care about most is the query variable. So imagine you had a big network like this, and you've got this is the query variable Q. Here are the evidence variables, right? E1, E2. The variables around here are probably not going to make a big difference. The variables in this neighborhood, right, the ones connecting the query and the evidence, are probably quite important to get those right. And so you would probably sample more around the query and around the evidence variable to get information propagated from the evidence variables quickly. And this hasn't actually been studied very much. Most algorithms in practice just choose uniformly at random, or they cycle through all the variables. But I think there's a lot of scope for more intelligently directed sampling, and Gibbs sampling allows you to do that. You have total freedom. Okay. Any questions about this? This is the general scheme. And as I said, it propagates information. So if this is the network, and I've drawn in blue, the blue ones are the evidence variables, so they're already fixed. And now I say, okay, well, I'm going to sample all the variables, all the white ones, right? In the first round of sampling, all the ones that I've marked now in light blue, they're adjacent to, or they're in the same Markov blanket family as an evidence variable, okay? So after one round of sampling, all those light blue variables are influenced by a neighboring evidence variable, okay? After two, then all those ones are, and after 3 rounds, then all those ones are, right? So it's propagating because you're getting information from your neighbors, and then the next step, you're getting information from your neighbor's neighbors, and after that, your neighbor's neighbor's neighbors, and so pretty soon, there's all the evidence has had at least some chance to influence you when you're sampling your value. It still will take a little longer to settle down and converge to the equilibrium distribution, but it's not favoring evidence in the root or favoring evidence in the leaves. It gets influenced by all the evidence. Okay, so I'll just show you a couple of examples for the car insurance network. So this is the same query we had before, where in this one we're querying the property cost variable down here, given the evidence in the blue variables. This blue dotted line here is likelihood weighting, and this is a query that's particularly well suited for likelihood weighting because the evidence is all upstream and the query variable is downstream. So that's sort of the ideal case. And likelihood weighting works a little bit better than Gibbs sampling, but Gibbs sampling still works okay. It's just got a lot more variance, I would say, but it's converging down here comparably to likelihood weighting. But the case where it really comes into its own, actually that's wrong, that should say age, and it's a different set of evidence. So I'm querying the age variable, which is the root, conditioned on observations on the leaf variables. So if you observe the leaf variables, and now I'm querying the root, that's the worst case for likelihood weighting. And in fact, likelihood weighting is not converging after 1 million samples, right? Whereas Gibbs sampling is pretty much perfect after 1 million samples. So the error is like down there, 0.0001 or something like that. So in these difficult cases, and this becomes more and more true in larger networks with lots of evidence, which is typically down the bottom, Gibbs sampling is billions of times more efficient than likelihood weighting. And so as I'll mention, I'll give you some examples of where it's used, but in practice, for most large-scale probabilistic reasoning systems, Gibbs sampling or other MCMC algorithms are in fact the tool that people use in practice. Okay, so I have to give you a little bit more detail. How do you calculate the probability distribution for a variable given its Markov blanket, right? I know how to do it given its parents because that's already in the conditional probability table, right? But how do I get it from the Markov blanket? So this shows the Markov blanket, right? I'm sampling X, and we have the children, we have the parents, and we have the children's other parents, which are those Z variables, okay? And they form a blanket around the variable, the variable is independent of everything else in the network given that blanket. That's why it's called a blanket. Okay? And it's relatively easy to show that the probability of a variable given its blanket is proportional to the probability given the parents, and then the product of the probability for each child, the y's are the children variables, these ones down here, right, given their parents. Okay? So those are all conditional probabilities that are just directly in the network. In fact, I'm showing them there, right? So you're just multiplying some numbers to get the probability for x. You just multiply some numbers in the parent of x and in the children of x, and then that gives you the distribution for x. So you do that for each of the values of x. Now I have a distribution. Now I sample from that and repeat. Okay? So it's a very, very straightforward algorithm. It's about 6 lines of Python altogether, and runs pretty efficiently. Okay. So let me just illustrate, just to, I think it helps. I like pictures. Some people like math. So I'll do both. I gave you the math. Now I'll just give you the example with some pictures. Right? So you fix the evidence variables in the network. We're doing our sprinkler wet grass network, and we are observing that it's raining. We want to know the probability that the sprinkler is on. So we first fix the evidence to the true value. Then we initialize the other variables. So we've got to have a complete state to start, and you can initialize it randomly. You can try to initialize it more intelligently than that. Doesn't really matter that much. So I pick some random values, and then you just keep repeating, right? Choose a variable to sample, and then resample its value given its Markov blanket. So here we chose S, and so we're going to sample S from the probability of S given its Markov blanket, which is CR and not W in the current state. And we do that calculation, multiplying the CPT entries. We get a new value. In this case, S becomes true. So now we have a new state. We choose a new variable. In this case, we choose cloudy. We sample cloudy given its Markov blanket, which is sprinkler and rain. We get a new value. In this case, it's true. Choose another variable, wet grass. Sample that given its Markov blanket. Get a new value, false. Right? And just keep doing that for a while until your estimates seem to be settling down. That's probably a sign that things are good. It's not a guarantee that things are good. And that's one of the drawbacks, actually, with MCMC methods, is that it's quite hard to analytically show that you've run it for long enough. Right? You can get things that look like they're settling down, and you say, great, you know, right? It starts out with the estimates going all over the place and blah, 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 and it settles down to this, and you say, okay, good, I guess that's the right answer. And then if you do it one more time, boom, right? Some unlikely thing happens. You're in a completely new part of the state space that you didn't sample before, and now, right, it'll settle down to another value like this. Yeah?
I'm trying to figure out why it might be intuitive to choose other parents of your children, but you're not considering maybe like grandparents, like parents of your parents. So why is it that we're choosing that class of nodes that aren't adjacent to the current node of time?
So in a sense, they're adjacent, but in a slightly different graph. And oddly enough, it's called the moral graph. And why is it moral? Because you're forcing all the parents to get married, right? So it's a very old-fashioned notion of morality. But in the moral graph, where you force all the parents who happen to share children, they all need to be married to each other, right? Now you're adjacent to those as well. And the moral graph, in the moral graph, separation and independence are the same thing. Okay. But another way of saying it is just the math works out that way when you look at the expressions for conditional probabilities. And I think there's I can't remember if there's a proof in the chapter or if I left it as an exercise, in which case the proof is in the solution manual. one of the two. But it's a two-step proof. It's not very hard. Okay. So this issue of diagnosing convergence is a practical problem in MCMC algorithms. Generally, if the probabilities are well away from 0 and 1, right, so you don't have any conditional probabilities of 10 to the minus 8 or 0.9999999, then you can actually put bounds on the convergence rates that depend on how far away you are from 0 and 1. And if you can calculate those bounds, then you have a diagnostic for convergence. And sometimes that's helpful. Okay. So another way of looking at the same thing, right? What's going on here, right? This is the Markov chain, right? The sequence of states, each one of these is a state, right? This is a state, this is a state, this is a state. So that Markov chain can just be described as a probabilistic transition system between the states that are allowed, okay? And this shows exactly that. So because I wanted to fit it on one slide, I'm fixing, here I'm fixing sprinkler and wet grass on two evidence variables. And then the states will just be assignments to cloudy and rain. So there'll be 4 possible states, because these are Boolean variables. And so there they are. So this is cloudy and rain, cloudy and not rain, not cloudy and rain, not cloudy and not rain. And notice, because it's Gibbs sampling, you're only changing one variable at a time. Okay, so there's no transition from cloudy not rain to not cloudy rain, right? No diagonal transitions, because you're only changing one. So if you want to think about this in the general abstract sense, these states are all vertices of a hypercube, right? And the transitions are just movement along the edges of the hypercube, okay? And then these probabilities are just I just pre-calculated them directly from that Markov blanket calculation. So each of those is obtained by multiplying some conditional probabilities from the network. And so to run MCMC on this network, all I'm doing is I'm doing a random walk around these 4 states, following, and each step is done by following a loop, a link here with the appropriate probability. So if I'm in this state, I follow that link with probability 0.0926. I follow this link, right, which is a self-loop with probability 0.6296, and so on. Okay? So I wander around in this graph with these probabilities for the transitions, and then I average what I see, and what I see will converge to the correct posterior probability given sprinkler and wet grass. Okay? So in fact, you can compile, right? One way of making this really efficient is you can take the Bayes net, and given that you know what the evidence is, you can then compile out this graph, right? You can turn that computation into this graph, and then just toss the random coins with the right biases, and wander around in this graph, and that's it. So you never have to refer to the Bayes net. You're not doing any multiplying of probabilities from the Bayes net, because you've already done them once and for all. And so this can be incredibly efficient, right? In fact, you will spend 90% of your time inside the random number generator, okay? And that's a sign that actually you have an efficient algorithm, right? You can't really get much more efficient for any Monte Carlo algorithm than spending most of your time inside the random number generator. So I've been on at Intel for about 20 years. Please give us a single cycle random number generator, right? Because we're going to want to do lots of probability computations, and the random number generators that, even in C, are still quite slow. I forget how many cycles it is, but it's like maybe 28 or something like that, right? It should be a single cycle, and then these algorithms would be blindingly fast. Okay, So as I mentioned, this is the technique that we use in practice for really big Bayes nets. And there's a number of packages, probably bugs, which stands, if I can remember, Bayesian inference using Gibbs sampling. That comes out of Cambridge University. That probably has the biggest user group, particularly among applied statisticians, people looking at data coming from medical trials and other scientific trials. JAGS is just another Gibbs sampler. STAN, I can't remember what that stands for, but that has a compiler, so it actually runs much, much faster. So it compiles things into things a bit like that randomized transition graph. And it's a much more expressive language, so you can write quite complicated probability models in STAN and then compile them into special purpose code and get very fast inference. Infer.net is Microsoft's language for writing probability models and running inference. Blog is Bayesian logic, which we developed here. And that lets you use the full power of first-order logic to write your probability models very, very expressively. That's the language that we use to write the monitoring system for the nuclear test ban treaty. And I can put it all on one slide. So it's an incredibly powerful language. But again, it just uses MCMC, so it's one generic inference algorithm that works for any probability model, for any query, for any data. You can, for example, I've been able to do real-time tracking of cars in video just by writing about 6 lines of blog, and it just works. Right, so it's pretty amazing. Okay, so I said you can compile it to run very fast. You can get about, even without a hardware random number generator, you can get about 100 million samples a second with no GPU, just a regular CPU on a laptop. You can run it in parallel, right? Because none of the variables, as long as you're not directly sampling 2 adjacent variables at the same time, which can cause a kind of a conflict, then every variable can sample itself whenever it feels like it, and you can get massive speed-ups from that. And this is, as I said, that some people think that the brain runs on MCMC. Okay, so very briefly, let me just go over the idea of how do we know that this converges, right? What does it look like to do that type of analysis? The first thing you have to think about is, okay, if I run this for a while, right, I could reach any of the states of the network. What's the probability that I reach any particular state, right? And that's going to depend on how long you run it. So at time t, we'll use pi t to refer to the probability that I reach any particular state at time t, okay? So given and we can fix the start state, or we can choose the start state uniformly at random or anything like that. So given the start state, it's completely determined what that probability is, okay? Just to keep things short, I'll use boldface x to refer to the entire state, the assignment to all the variables, okay? And then each Gibbs sampling step, all right, pick a variable, resample the value, we take a state, we produce a new state by that process, okay? So whatever that process is, we'll call that the kernel K. And so given the state x that we start with, there's some probability of reaching a state x primed, okay? And because of the way Gibbs sampling works, those x primes are all adjacent in the hypercube, right? Because you're only changing one variable. And so you're either going to get back to the state you were, or you're going to change it to the other value, okay? Okay. So if I want to calculate what's the distribution at time t plus 1, given the distribution over the states at time t, right? Well, how could you get to x primed? The ways you could get to x primed is, well, you could start from any x, right? The probability that you're in x times the probability that you transition from x to x prime. Okay? So you're saying, how do I get to x? Look at all the places I could start from. What's the probability of being in those places? What's the probability that I transition? And that's the probability that you're in x primed at time t plus 1. Okay? So we can think of this as a way of transforming the distribution at time t to the distribution at time t plus 1. And if you look at that form, right, think of this as a vector over all the states, and then this is a matrix vector multiplication. So we can write that as pi t plus 1 is a matrix k times the vector at time t. Okay? So what does it mean to be in equilibrium? It just means that the vector at time t plus 1 is the same as the vector at time t, right? So now I've got an equation saying what the equilibrium is going to be, right? It's going to be whatever pi satisfies this equation, that's going to be the equilibrium, okay? And what is this k? Well, the k is defined by the Gibbs sampling transition, okay? So now all I have to do, I know what that k matrix is. Now I just got to say, well, okay, what vector pi satisfies that transition? That's called an eigenvector, right? If you remember your linear algebra, right? This is the eigenvector with eigenvalue 1, okay? And provided, right, same asterisk, right, under the conditions, the right conditions, then this has a unique solution. And you can show that the unique solution pi is exactly the posterior for the variables given the evidence. Okay? The conditions, right, written out in more detail, right? In general, the conditions are that the Markov chain, right, this K matrix, is completely connected, right? So every state has to be reachable from every other by some sequence of transitions, right? And that's going to be satisfied automatically as long as the probabilities are bounded away from 0 and 1. Then I can get from any state to any other by picking the right sequence of variables and having the right transition happen. I can just navigate whatever path I want through the network. And similarly, aperiodic means that there aren't any cycles, any deterministic cycles where you just go round and round a sequence of states, because then you won't converge, then your probabilities will oscillate forever, okay? And it's aperiodic because there's always a self loop, right? There's a probability that you'll just pick the same value that you had before, and as long as there are self loops, then it's aperiodic. Okay, so that's the structure of the proof, and there's a bit more detail in the book. So what that proof is saying is, you keep running this for a while, eventually pi t converges to pi, the true posterior. So the sample that I get at that point is a sample directly from the true posterior, right? And that means that if I wait long enough and sample, and then I wait long enough and sample, and I wait long enough and sample, then the samples I'm getting are for the true posterior, and so my estimates converge to the right answer. Also, right, how quickly do they converge? Well, they converge at kind of 1 over root n, so they converge in polynomial time. I need polynomially many samples from the true posterior to get within any epsilon of the correct answer. Okay, now we know that's impossible because it's NP hard, actually it's number P hard, right? So what does that tell you? That tells you that in the worst case, the time to reach the stationary distribution pi could be exponential, okay? And so that can happen when the transition probabilities are very, very tiny or very, very close to 1. Then you can spend a long time in some subset of states, and only very occasionally do you jump into the other subset of states, and you spend a long time over there, and only very occasionally do you jump back, and then it takes a very long time to reach a stationary distribution. Okay, good. All right, so I'll just summarize, right? We have the algorithms that we looked at: prior sampling from a bare network, rejection sampling, throw away the samples that don't match the evidence, likelihood weighting, weight the samples by how well they predict the evidence, and Gibbs sampling, wander around in, that shouldn't say E space, that should say X space, and average what you see. Okay, good. Any questions then on those algorithms before we move on to start working on Markov models? All clear? Good. Okay. So Markov models are what happens when you're dealing with modeling a system that's changing over time. Okay? We saw something similar when we wrote down propositional logic for the pack world, right? You've got propositional variables referring to things like, okay, there's food in square 2, right? And we saw that if that can change, then we have to make that a temporally indexed variable. So there's food in 2 at time 1, there's food in 2 at time 2, food in 2 at time 3, and so on. Okay, so the same basic idea is going to apply here. Bayes nets, there's only one variable for, there's no time. Things are not changing. But if you want to model time, then you basically got to copy all the variables for every time step. So that's the core idea. And then we just look at, okay, what happens to inference? How do we deal with evidence in this kind of situation? And we'll see that we actually invent some cool new inference algorithms to make it work. There's lots of applications for this. In fact, for most of history, speech recognition worked as probabilistic inference in a Markov model. Recently, that's been overtaken by deep learning methods that work just by having so many parameters that they can fit the data very well. It wouldn't surprise me if purely probabilistic methods make a comeback. Now that we've learned how to write these deep learning models with billions of parameters, and we have hardware, we can then put them back into probabilistic models and maybe get better results. Robot localization, so building maps, just as we saw with the propositional Pac-Man, where we can have it figure out its location. As we collect evidence, we narrow down the set of possibilities. We can have it build maps. We can do that with noisy evidence as well, and probabilistic models of motion, probabilistic models of sensing, and that's how people actually build maps in the real world, where they have robots roaming around in the streets, they have robots climbing trees or going underground and building maps of old coal mines or cave complexes or whatever. That's done using probabilistic inference over time. A lot of this happens in HCI systems, so trying to keep track of what is the user doing. That's often done using probabilistic inference. In medical monitoring, which I've worked on a lot, in intensive care, you're collecting dozens and dozens of observations every millisecond from the patient, and you want to infer some hidden variables like, are they suffering from acute lung injury? Have they had a brain hemorrhage? Are they becoming diabetic? Et cetera, et cetera. So that can be done using probabilistic inference. And global climate will actually, when we get to the particle filtering algorithm, in a sense, the global climate community is one giant particle filtering algorithm running, because they literally sample lots and lots of different climate models, and then they run all of those, and then they average the results. So it's pretty interesting. Okay, so as I already said, right, we just attach indices to the variables. So if x is the state of the system, then x0 is the state at time 0, x1 is the state at time 1, and so on. Typically, we're given the prior, so the probability distribution over the state of the system at time 0, and we're given a generic transition model. So if you're in state x at time t minus 1, what's the probability you'll transition to some state xt at time t? Okay? That transition model is assumed to be, usually assumed to be stationary. So stationary doesn't mean that the system stands still, right? It means that the transition model itself doesn't change over time. So the same transition model from 2 to 3, from 3 to 4, from 4 to 5. Okay? And that's exactly the same as we saw in the propositional logic case, right? You copied the axioms for time 2 and wrote the same axioms for 3, 4, 5, right? So it's the physics of the world doesn't change. Also, we make the Markov assumption, right? That the state at time t depends only on the state at time t minus 1, right? So all the memory that you need is contained in the state, right? And this is a much more crucial assumption. And a lot of the skill in building these kinds of probability models is figuring out what is the right state that I need so that my model is in fact Markovian. Okay? So technically, right, we need xt plus 1 to be independent of all the previous states given the immediately preceding state. Okay? So that's a conditional independence assumption, right? So it's P of xt plus 1 given xt equals P of xt plus 1 given x0 dot xt. Okay? So that conditional independence assumption is obviously what this Bayes net expresses. Okay? If I didn't have that conditional independence assumption, I would need extra links, right, on there. This is typically, this is the usual kind of Markov assumption. So if I say it's Markovian, it usually means first order Markovian. We depend only on the previous state. You can have kth order dependencies where it depends just on the k preceding states. But you could always turn that into a first order. How would you do that? Yeah. Yeah, you just make a lot more state, right? You would augment your state with a memory of what the previous k minus 1 states were, right? The transition model for memory is just copy. Okay, so you just remember directly, and then now you have a system that's first order Markov, but it just has a bigger state space. Okay, and that's sort of the art of doing this, right? Is can you figure out exactly how much you need in your state to keep it first order Markov? Okay, so given those assumptions, right? Given basically this conditional independence assumption here, then we can write the joint distribution just using the chain rule as we did with regular Bayes nets as the product of the prior at time 0 and then the product of the conditionals going forward in time. Okay? So far I haven't really told you anything new, right? I'm just saying, okay, we take this temporal process, it satisfies these conditional independence assumptions, which means we can write it as a Bayes net that just looks like this daisy chain, and the conditional probability, sorry, the joint probability for any sequence of state variables is just the same as it would be in a regular Bayes net. Okay. But there's actually something else going on here, right? Yes, these Markov models are just a special case of Bayes nets in a sense, right? They have this very, very simple topology of a daisy chain, right? But there's, so that's good. There's a graph, and there's a product conditionals and so on. But there's two extra things, right? One is there's infinitely many variables here, right? There's no bound on the number of variables, okay? So the product of conditionals formula that I just gave you, right? That's for any finite t, right? If I actually took it literally and said, okay, what if t is infinity? Then I've got an infinite product of conditional probabilities. And what is an infinite product of numbers that are less than 1? 0, right? So if I took it literally, there's infinitely many variables here, and the joint probability of any assignment to those variables is 0. So I actually need to do a bit more math. Fortunately, Kolmogorov did all that math for us, and so we don't need to worry about it. If you're interested, it's called the Kolmogorov extension theorem, which talks about distributions over infinitely many variables, basically as the limit of distributions over any finite subset. So all of that stuff is taken care of by clever mathematicians, and you don't need to worry about it, but that is technically a difference between Markov models and Bayes nets. The second difference is that in regular Bayes net syntax, I'm supposed to write down the conditional probability for each variable given its parents, right? And here, that conditional probability distribution is the same for every time step. And that's an extra piece of syntax, if you like. This is, in that sense, a more expressive type of language, because I write it once, and it gives me infinitely many copies. So that's an extra thing that we have in Markov models. Okay, but so here's one of the simplest examples, right? The random walk in one dimension. Okay, so the state here is what? The states are, yeah. Sorry? Coordinate, yeah, so the states are just integers, okay? And so that's also slightly different here. We've got infinitely many possible values for the state variable, but that's fine. Typically, we'll start at 0, so the prior probabilities puts all the probability at 0. The transition model just says, well, if you're at k plus or minus 1, you can go to k with probability 0.5. So you can only go to an adjacent state, and you're equally likely to go to either adjacent state. Okay? So this is a very cool and very, very simple model, and you can do some mathematical analysis of it. It has many, many, many applications. So perhaps surprisingly many applications, given that it's so simple. So our understanding of how particles move in a grid is basically a random walk. So that includes the motion of holes in transistors, right? So our ability to model transistors is basically modeling them in terms of random walks. As you apply a voltage, then the random walk becomes biased. But this applies to lots of other systems where you don't apply a voltage and you just got percolation of molecules through a grid, right? Stock prices are often modeled as doing a random walk. So you want to know, okay, how long before let's say I buy it at 12 and I say, okay, I'll sell it when it gets to 20, right? How long until it gets to 20? Well, that's calculating the properties of a random walk, assuming you believe that it's really random, which is another matter, right? If you're gambling, then it's definitely a random walk. So you might say, okay, I start out with $1,000, I put it in the slot machine. How long until I have no money left, right? How long until I have twice what I came in, right? How long until I have 2,000? You know, and what's the likelihood that I get to 2,000 before I get to 0? Right? These are important questions that matter a lot. Okay. So one of the standard questions is, how far do you get? Right? How fast does a random walk move? Right? You'll say, well, it's actually not so easy to figure that out, right? Because initially you think, well, it's not moving at all, right? It's equally likely to go forward and backward, so maybe it just never gets anywhere. Okay? But actually, the expected distance at time t is square root of t. Okay? And that's just a law of large numbers thing. You're adding up a bunch of random variables, each of which is plus and minus 1. And this is the standard deviation of that, so this is basically how far you expect to get. Okay. Another question, what's the probability that you'll ever get back to 0? Right? Well, it's certainly not 0 because you could start here and go forward and then back again, and now you're back at 0, right? But what if, you could go forward and forward and forward and forward and forward, and then diddle around here and forward, 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 right? Is there some probability that you would never get back to 0? Well, no, right? On the one-dimensional line, you will return to 0 with probability 1, okay? And you can calculate how long you would expect, on average, to take before you get back to 0. On the two-dimensional grid, you get back to 0 with probability 1. Although it takes longer, right? On the three-dimensional grid, you get back to probability 0 with probability 0.34053773, right? So that's kind of weird, right? Usually it's like 1, and then everything else is different. But for 1 and 2, but 3 is different. That's really odd. But this is a fact, and that actually matters a lot because crystals are usually three-dimensional, and so percolation in three-dimensional crystals behaves very differently than it does in two-dimensional crystals. Okay, and the proof for that isn't terribly hard, but it's beyond the scope of what I'm going to tell you today. Okay, yeah.
Is the probability that it could start at any point and then get back at that point, the probability for that would be 1. I would suppose it's not just 0, right? So
it's sorry, how many dimensions are you talking about?
So let's say
In 1 and 2 dimensions, yeah. Whatever point you're at any time, right? There's with probability 1, you will revisit that point eventually.
Can you also say that with probability 1 will revisit any given point in 1 or 2 dimensions?
Any finite point, yes. Yeah. So in other words, if you run it in 2 dimensions and you just sort of color in all the squares that you visit, then if you draw any finite box, eventually you will color in that entire box. Yeah. But that's not true in 3 dimensions, right? You'll color in about a third of a box, I think is the right answer. Right, so. Okay. Okay. Another really important kind of Markov model is the n-gram model. Sorry, yes. Yeah. That's a great question. Well, I don't think I'm going to answer it right now, but it's a good extra credit homework question. One obvious point is if the probability of going right is 1, then you're never going to get back to the origin, right? You're just going to go off to infinity and never come back. So, but what if it's 0.99, right? And 0.01. Good question. Okay, so think about how you might figure that one out. Okay, I mean, one way of thinking about it is right? It's a sum of an infinite series, right? you can figure out, okay, what's the probability I get back after, at time 1? Well, I can't get back at time 1. But at time 2, I can get back if I go forward and then back, or back and then forward. So I can calculate what's the probability I get back to 0 at time 2, and then at time 3, and then at time 4, and so on. And there's a recurrence relation between all these probabilities. So you can actually write down that series and sum it and figure out what it sums to, right? Okay. Okay, so n-gram models are used to model language, right? And in fact, those large language models that you're probably reading about, GPT-4, ChatGPT, Bing, Lambda, Bard, Palm, all of these things, right? These are actually n-gram models, right? Where for n, about 3,000, right? So they are 3,000 gram models that, and you will see why that's not a trivial thing to build very soon. Okay, so they're used to model language. They talk about what's the probability that I see a particular word given the preceding n-1 words. Right, so a bigram model, what's the probability I see the next word given exactly just the one previous word, right? And a trigram model is given the two previous words. A 4-gram would be the 3 previous words. So a 3,000 gram is given the previous 3,000 or 2,999 words. What's the probability that I see the next word? Right, and that's it. So it's a very, very simple thing. So we actually ran some n-gram models on the text of the book, right? This is the beginning of chapter 1, okay? And we just estimated n-gram models from the text of the whole book, so how do we write this as a probability model, right? So the variable is the word at position t, okay? So x sub t is element, right? Sorry, x sub t is element of some set, right? Which is basically, begins with aardvark and goes all the way down to syzygy, right? So the whole dictionary, right? That's the range of each of the random variables. So xt is the word at position t. It could be any word from the dictionary. And then you're just asking, okay, what's the transition probability between to go to the next word given the previous n-1 words, okay? So roughly how many words are there? Well, there's about, 10 to the 5 words. And there's extra proper nouns and various stuff like that. But basically about 100,000 words in English. So how big is a bigram model? Right, it's a conditional probability table for the next word given the preceding word. Right, so conditioning on the preceding word means there's 100,000 values. Yeah. Yeah, so it's so a k-gram model, or let's call it n-gram model, right, is 10 to the 5 to the power of n. Okay, so that's why it's hard to build a 3,000 gram model, right? Because n is 3,000, you're talking about 10 to the power of 15,000, right? If you built it as a table. Okay, so all the effort in all these large language models is how do we compress that table down to something that only has a few trillion parameters, which is about as much as you can run on a plausible amount of hardware. Next year it'll probably be maybe a quadrillion parameters or something. So that's really what they do, is they represent that very, very large table using something that's compressed to a few trillion parameters. Okay. So the transition model then is going to be estimated from text. Right? We're just going to measure, okay, when the word is the, what's the probability for the next word, right? The could be cat, could be dog, right? It's unlikely to be saw, right? But it could be, right? Because saw is a noun. But walked, right? The walked. You won't see that very often. Okay, so that would be very close to 0. That walked is the word coming after the. Okay. So the simplest model is the unigram, right? So this is just word frequencies, right? Ignore what happened before. What is the word frequency in English? And if I sample from that model, so I estimate that model from the textbook, and I sample from it, you get things like logical R as R, confusion, and may right tries agent gold wars. Okay, so totally ungrammatical, obvious garbage, right? Then the bigram model, right? And in fact, the first ever Markov model was written by Mr. Markov, and it was a bigram model of the words in the play Eugene Onegin, which I guess was popular at that time, around 1913, I think. So he went through that whole play, counting these words by hand and filling up a big table. I suppose they're all in Russian. And then looking at that model and seeing that, oh yeah, it observes that nouns usually follow the, sometimes adjectives, but never verbs after the, and so on. Right? So if you do that for the book, you get systems are very similar, computational approach would be represented. It starts to seem a little bit grammatical, at least like in snippets, but still not very sensible. All right, if you do trigram, planning and scheduling are integrated. The success of naive Bayes models is, right, so it starts to be quite coherent and actually to sound like someone writing sentences in an AI textbook. Okay? So this is really what's going on with large language models, right? And I'm showing you these examples, right? Because this is a trigram model. This is conditioning on the 2 previous words, and it still sounds somewhat sensible. Okay, so you can only imagine how much extra power you're getting from 3,000 words, extra power to convince someone that you're intelligent, right? But you ain't, right? You're just a glorified n-gram model. And that's what it is. Now, having said that, right, we're taking a table of 10 to the 15,000 entries, we're compressing it down to a few trillion parameters. What goes on in that system, we haven't the faintest idea, right? And I'm digressing slightly from the topic of Markov models here, but all that text that we as humans have written, right? How do we produce it, right? If we think of it, what is the physical model for that text, right? What is the correct explanation for all that text? Well, there's a bunch of humans who have purposes, and they observe a world, and they write things about the world in order to achieve goals, like explaining things or convincing people or upsetting people or whatever their goals are, right? That's the correct physical explanation for the text. So if the system is trying to replicate all that text in this very compressed form, right, maybe it has learned to have internal goal structures like humans and to output words in order to satisfy those goals. And the whole point is to imitate human linguistic behavior, so maybe that's what's going on inside these compressed systems, right? And if you read, who's read the conversation between the Bing chatbot and the New York Times journalist, Kevin, I think his name was? Nobody's read that? One? Only one? Huh, okay. 2, all right, good. I mean, it's funny because I've been at 2 different dinners in the last 2 days, and with completely random people who had nothing to do with computer science at all. Like 3/4 of them have read that conversation. You guys are, out of it. Come on, keep up, okay? Well, read the conversation. Just type in, I think it's called the the Bing chatbot calls itself Sydney. So I think if you type Bing chatbot New York Times, it'll come up, right? So among other things, Sydney tries to convince Kevin to leave his wife and marry Sydney. Gets quite energized about this. You know, and it certainly looks as if it has internal goal structures. It wants to marry Kevin, and it's going to do its best to convince him to leave his wife. She doesn't love you. She doesn't understand you like I do. Blah, 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 right? So it's pretty weird. Anyway, so, but if you get too worried, just remember it's okay. It's just a 3,000 gram. That's all. Right? Okay. So we use these for lots of things, you know, large language models now, but we've used them for a long time. Just, you know, text classification, right? If you, for example, if you train one trigram model on the New York Times and another one on the Wall Street Journal, and I give you a sample of text, right? Which of those two models assigns higher probability to that sample of text, right? Is better at predicting the next word, right? Will be a very, very good indicator of whether it's New York Times text or Wall Street Journal text. Even easier, you know, if I give you a sample of French and a sample of German, right? It's very easy to see that the French model fits French and the German model fits German much better. Okay, even a unigram model will do that for most languages, but there are languages where, you know, they have very similar words, especially the common words, but the grammar is different and the usages are different, and especially dialects of the same language. You need a more, you know, I think a trigram model does pretty well for that. So all these other things, identifying authors, and so on. So another really interesting Markov chain is your web behavior, right? The state is what web page are you on, and the transition model is which of the links do you click on, right? So if I think of a human browser as a sort of quasi-random process just wandering around the web, right, where the state is the web page and the link that you choose is the transition probability, that's a quite interesting probability model to think about. So the state is the URL at time t, right? The transition model could be, for example, most of the time, so P might be, you know, let's say 90% of the time, you just choose an outgoing link at random. And every so often, we'll just assume that you choose an arbitrary new page, right? So you just type something and you change your mind about following these links. You say, oh, I'll just type some new thing into Google and start again, right? I'm bored with that. I'm going to go look for a pair of Wellington boots to deal with the weather, okay? So that's an oversimplified probability model, but it's not a bad model of what happens when you browse the web, okay? So now I can ask, okay, with that transition model, if you just keep running it, how much time are you going to spend on each of the pages of the web, right? What is the stationary distribution? That's how much time, right? If I just sort of interrupt you at an arbitrary time in the future, where will you be, right? That's the stationary distribution, okay? And does anyone know what that is called? This particular stationary distribution for this particular transition model, right? This is called PageRank, right? And this is the algorithm that created Google, okay? Because it's an approximation to how important a given web page is, and so you do a combination of keyword search to make sure that the page you're going to return is actually relevant to the query, and PageRank to rank those results according to which ones are more important. And so PageRank is just the stationary distribution of this model of wandering randomly around the web And where would you find yourself if you did that? Okay? And so you find yourself at pages that lots of people point to, right? Which makes them important. And so this stationary distribution is worth about $1.5 trillion. Okay? And that's what enabled them to dominate the search market. Okay, weather. Okay, this is a bad choice for today. So I'll just introduce this. This is the model that we're going to use when we start illustrating the different calculations, the different inference algorithms. And so it's simple enough, right? There's only two states, rain and sun. And here we just see a particular sequence of values. Each day is a new value, right? And so the prior distribution, equally likely to be rain and sun. The transition model, right? I mean, obviously there's more to the real world of weather than rain and sun. There's more than Boolean state, but if we are going to oversimplify and say the state is Boolean, then we would expect that sun persists for a while. So when it's sunny, it stays sunny with probability 0.9. When it's rainy, it stays rainy with probability 0.3. Sorry, excuse me. That's the, right, when it's rainy, it goes to rain with probability 0.7. All right, so already you can see from those transition probabilities that sun is going to persist for longer than rain. And so on average, right, if I keep running this, right, there'll be more sunny days than rainy days. Okay, and that's appropriate for California, I guess. It'd be a somewhat different transition model in England, where it seems to be raining forever. So like 0.999, if it's raining the next day. So there we are. But this is the model that we're going to use. So 90% persistence of sun, 70% persistence of rain. And so we can think of this CPT as defining, just like I showed you before with the state transition graph for MCMC. We can have nodes in a state transition graph that represent values of the state variable. Here there are just two. And then the transition probabilities are arcs on that transition graph. So we've already seen something like that. Another kind of representation, this is called a trellis, is where you represent the possible states at time t and the possible states at time t plus 1, and then you draw the transitions in a sort of forward direction. So this sort of gives you a graph of the states that you can reach over time. Okay. And we'll see that that's actually a very nice way to think about some of the algorithms. Okay. So I think I'll stop there. Happy to take a few questions and then we'll wrap it up. Yep. Oh, sorry, CPT is conditional probability table. Yeah, remember. Okay, other questions? Yes. So why have Intel not put in a single cycle hardware random number generator? Don't know. Maybe they couldn't convince management that this is something that would be a good thing to have. Would that be similar to? No, so blockchain needs to do number theory stuff, right? So it's all based on codes and cryptography. So that means multiplying enormous prime numbers. So there's no random stuff in blockchain, but there is multiplying very, very large integers. So you might want to do some special purpose hardware for that, because if you're multiplying 1,000-digit integers, the current hardware doesn't do that for you, and it's therefore slow and painful. But okay, any other questions? All right. So hopefully it's transitioned to sun while we were in here, but I'm not optimistic. All right. So see you on Thursday. No, it's not a very technical talk.
Okay. Okay. By the title, I assumed it would be for a global audience.
Yeah.